Now, this is the analysis that we had done before when we looked at the construction of SARIMA models. Okay, we read the data, and that's the electric production data. We made it into a time series. Then we looked at the Box-Cox transformation, and ended up taking the logarithm of the production, okay, of electric production. From there, we computed the ACF and the PACF. Decided we needed to take a difference of order 12, and then try to model that. And the model didn't turn out to be right. Okay, the model didn't turn out, although the autocorrelation function looks good. This autocorrelation function looks good. The p-values look very low. It looks good, although there's a couple of significant autocorrelations here. So one way to hint you in terms of what type of model you should follow. Remember, we saw that in one of the presentations. I believe it was in presentation 08. Okay, when we looked at model construction, and we said that if we don't struggle a little bit to get the right model, we can analyze the residuals, and the residuals will tell us what type of model we should use. Okay, I'm going to remind you of that with I'm going to open that presentation. Let me see here. It's number 8 in model building, model building. Okay. Here we said if we feed the wrong model, it's around here. Let me see where it is. Okay, in slide 11. See, if the actual process for the model is phi of b WT, WT is a series that has already been transformed and has been centered. Okay, then if this is the right model, but what we identified is this model with a phi prime of b, which is a different polynomial than this phi of b, and theta prime, which is a different polynomial time applied to bt, where bt is not white noise, which is the case that we have now. Then we can determine what corrections to do with the original model that we fitted if we analyze the residuals of this model. That's a wrong model. Okay, since bt is not white noise, then it will follow a behavior that can be expressed by a difference equation, also by a model of the form theta prime of b, phi of b, bt equals to theta phi prime of b, theta of b, at. Okay, so where at now is white noise. So the fact that we identified this model, then that tells us what corrections we should do to this original model here, to the original model that we fitted, to this model. Let me go to my Zoom here. Okay. Once we determine what's the right model for B, here we have determined what the right model for B is. Let me. Here's the right model for B, right? That's the model for B. Now, let's see, I'm drawing here and you cannot see what I'm drawing for some reason. Let me try. No, it's not drawing on the screen. But anyway, this is the model for B sub t, so that it's a model where the residuals are really white noise. And so the correction, we just express bt as phi prime b theta of b times theta prime inverse phi of B inverse applied to AT. We replace that in this equation, and we know how to correct the model. Now let me share my iPad here to show you the rationale here. We saw an example, right? If the model is this one, but we identified this model, that is, we identified an MA1 model, but BT is not white noise, then BT will follow an ARMA 1-2 process that will be given by this. 1 minus theta B, BT equals to an MA2 polynomial applied to AT, and we can use that to correct. So we replace BT. So BT would be equal to this polynomial, MA polynomial, times 1 minus theta B inverse, right? 1 minus theta B inverse times the MA2 polynomial. When we replace that in the equation, in this equation here, when we replace BT by what it is expressed in terms of this model, then the 1 minus theta B comes as an inverse here on the left side of the equation. And that tells us that we need to add an autoregressive term, right? That's what it's telling us. So now let me go back. I'm going to stop sharing here, and I'm going to share my screen in the iPad. Okay. This is the electric production data. This is the model we identified, right? We identified 1 minus phi B minus phi 2B, and then a seasonal component here equals AT, alpha T. Alpha T is not white noise, right? Excuse me, let me get it here. Alpha T is not white noise. So if I go back to the script, let me go back to the script. I'll stop as mentioned here and go back to the script. The residuals, we know, we saw that they are not white noise. So we identified a seasonal model with 2 autoregressive terms, 2 on the non-seasonal part, 1 difference, and on the seasonal component, 2 autoregressive terms and 1 difference also on the seasonal components. Now that's not the residuals, because of these p-values, are not white noise. So what I can do is I try to model the residuals. So the residuals are given by the element residuals from the model. Okay. It's a time series also, because that's the residuals of the original model. If I plot the residuals, now, of course, they are centered around the constant line because they have mean 0. And if I look at the ACF function for the residuals, I can try to identify a model for these residuals, right? I can try to identify a model, and it looks like the model that we have for their residuals. Look at this this spike here. That's on the ACF. I have, this is happening at lag 1, 2, 3, 4. This is happening at lag, what's that? This is 12, 11, and 10, roughly. Then we have here happening, this is noise, but we have something happening at lag 24 in the ACF. In the PACF, we observe a similar behavior, okay? In the PACF, we observe a similar behavior where we have the significant terms are around here, near the lag 4, but start at lag 3, and then it's all noise up to 3 years later. 3 years later, that's too long, that's too far away, okay? So I can assume that this could probably be noise, or due to some spike in the original series or whatever. So from here, I can think of, for the residuals, as a model of the form on the non-seasonal part, could be an AR2, okay? Could be an AR3, but we could start with an AR2, and also an MA2 on the non-seasonal part. And then we don't need to take a difference here because the series is already centered. Then on the seasonal component, I do not have seasonality of order 12, but I may have seasonality of order 3 or 4. Since we're talking about monthly data, it would make probably more sense to think of a 3 as a seasonal element that every 3 months. So I can try that model, okay? And I'm going to try this model, which is an SARIMA 202, 101. Why 1 in the seasonal part? Because we have one significant lag here at lag between 3 and 4, and also here. The same thing is happening here in 3 and 4. So that's why I consider 1 here. Okay, let's see how this model fits. And the model is not a perfect fit, but it roughly it sort of more or less fits, right? It's close to the p-values are very small here. So, but the ACF looks very reasonable. I could try to improve this model, but all I want to do is get a guide in terms of what type of changes I need to make to the original model that I did that I assumed at the beginning, and to try to get a better fit for the original series. Again, I could try to, since I have very low correlations here, I could have a 3 here, and see if that improves. That improved, okay. And my parameters, AR3 is significant. No, it's not really significant. AR3 is not significant. And MA1 is significant, okay? So I could try removing 1 here, okay? Because the MA2 is not significant. And then the seasonal part, I may try to eliminate one of them, and I could eliminate the moving average element, okay? Try that, and now my residuals look better, right? My residuals look better. And now the p-values look more reasonable. And I ended up here with a model of the form. This will be what? This will be a SARIMA 301 1003. Okay, that will be that's SARIMA. Now let's look at the coefficients. And again, the AR3 is not significant. Okay, the AR3 is not significant. And the moving average term of order 1 is not significant either. Okay, the mean is significant, so I cannot remove the mean. But then I can try to fit it without an AR term here. It doesn't matter. I can leave the thing here as a seasonality 3 because I'm not fitting any difference or anything like that, right? Now the AR2 is not significant, but the AR3 is close to significant. It's 9%, and the p-values look good, right? The p-values look good. So this may be then, and now I may try to remove the SA3 and put an AR2 there. The model doesn't look as good as the other one, but there's only one. None of the p-values are less than 0.05, particularly at the beginning. And now, if you look at the parameters, those are significant, right? Those are significant. All the AR1, the AR2, and the MA1 is significant. Okay. So now, what do I do then? Then I'm going to go back to my iPad here. So that will be a SARIMA 201, and then no, I don't have any seasonal terms, okay? So in fact, I can remove this whole thing. But I leave it like that. It'll be just that, because I don't have any seasonal component here. So it's a 201, okay? And I have identified here as Arima folders 2, 1, 0, 2, 1, 0, 12, right? Now, I'm gonna go back to my notes. And I'm gonna add a page here. I'm gonna stop sharing here my screen. And I'm gonna start sharing from my iPad. Share my screen. Okay. So the model that I identified initially is a Sarima, 210, 210, 21012, right? That's the model that I identified originally. That is the model that I identified for my series. Let's say that my series here is WT is 1 minus phi 1 b minus phi 2 b squared times and then the first difference, right? I have first difference here, and I also have a seasonal difference for the 12. That applies to WT equals to 1 minus, and then the model on the moving on the seasonal component is an AR2, so it's 1 minus theta. No, this is not theta because we're talking about here. This is the AR part, so that we use the capital phi. And we have an order 2 model here, phi 2, phi 1, b to the 12 minus phi, I can call this phi 12, and phi 24, b to the 24. Okay. No, that's the seasonal. That's the AR. That's the seasonal part. Hold on a second. Let me move this thing here. Okay, and then I'm going to take, this is part of the autoregressive component. So I'm going to select this. Yeah, paste it here. Then the first difference and the 12 difference of WT equals to what? Equals to AT, right? Because I don't have any moving average term in the original model that I identified. I don't have moving average terms on the non-seasonal part, and I don't have moving average terms on the seasonal part, on the seasonal part. So I only have here what I'm going to call here alpha t. Now, alpha t is not white noise. But we identified already a model for alpha t. We identified a model for alpha t. So I'm going to go, the model that we identified for alpha t was Sarima 201. Okay, alpha t has a model of Sarima 201. This is actually an Arima 201. So my model for alpha t is going to be then 1 minus, I'm going to call this thing phi 1 prime, phi 1 prime b, minus phi 2 prime b squared times alpha t equals to 1 minus theta 1 b, theta 1b of AT, where AT is white noise. AT is white noise. That's the model, because that's the model we identify for the residuals, and we can see that with that model, my residuals, the residuals I get are really white noise. So all I have to do now is replace alpha t. So from here we have that alpha t is equal to 1 minus phi 1 star b minus phi 2 star b squared to the minus 1 inverse times 1 minus theta 1b at. And I replace that expression for alpha t in this equation here. So what I have now is in my original model, which I have is equal to alpha t. I've replaced this thing there, okay? So I'm going to take this whole thing. Let me first clean this thing a little bit. And put this thing, and I'm going to cut it. And I'm going to select this. Move it upward a little bit, so I have more space down here. So I'm going to replace this thing. I'm going to select this equation, but instead of making it equal to alpha t, I'm going to make it equal to what alpha t is in terms of the model. So that's going to be equal to alpha t, and alpha t is 1 minus theta 1 star b minus theta, minus phi 1. It's phi 1. Phi 1 star b minus phi 2 star b squared inverse, times 1 minus, I lost it there, time, this is to the minus 1, times 1 minus theta 1 b at. Okay, so now I do it, but what I do now is I rewrite this thing, I put this thing on the other side of the equation, and what I get is now, I'm going to avoid writing so much, so what I'm going to do is I'm going to get this, copy it, and paste it here. And then I'm going to do the same thing with this one. I'm going to type, but this I'm going to put it not to the minus 1, but I'm going to put it just with the, without the power on the other side of the equation. So I'm going to say copy, and then paste. I have this polynomial, and then I do have times the first difference. I should have, well, you can ignore that line, because if I erase it, I'm going to erase more things here. Okay. Times the first difference, and the first difference, the first seasonal difference of order 12, that multiplying WT, and that's equal to 1 minus theta 1b at. So if you look at this product, look at this polynomial times this polynomial. What I get is a polynomial of order 4, right? For the non-seasonal part, the phi ones are components for the non-seasonal part. Okay, so it looks like an AR4 on this side. I'm gonna abuse the notation here and I'll say this looks like an AR4 because I have a power of 2 and a power of 2. That will give me a power of 4. And then I have on the seasonal part, I'm gonna put a seasonal AR of order 2 with seasonality 12. Okay, that's what I have, times my first difference, times my 12th difference, the seasonal difference, and that's equal to an MA, non-seasonal MA of order 1. Okay, so this could be a model to start fitting, to correct the other model. This is after some iterations, but what it tells me is this is an AR4. This will be S Sarima 4, because I have a fourth order autoregressive polynomial, then one difference, one non-seasonal difference, and I have 0 moving average terms here, right? On the non-seasonal, no, I'm sorry, on the non-seasonal part, I have one seasonal term. I have one seasonal term. And then on the seasonal part, I only have two terms, autoregressive terms, one seasonal difference, 0 moving average terms, and seasonality of 12. Okay, so I can try to fit a model of the form 4, 1, 1, and then it'll be 2, 1, 0 of seasonality 12. I'm going to stop sharing here from my iPad, and I'm going to go back to the script. Okay, I'm going to start sharing my screen. So I'm gonna feed this model to the same data, a 411, 210, 12. Okay, and this is my starting point to correct the model that I can fit. Now, if I'm sorry, I selected only 41. Okay. So if you can see here, the p-values improved. My ACF of residuals looks very good. My normal plot of residuals looks very well, right? So I have found how to correct the original model, just analyzing the residuals from the fitted model that did not have white noise as the residuals. Okay, so that's very important, because when you make a mistake identifying a model and you get a model that doesn't give you white noise, you can analyze the residuals and from there obtain what the model should be to correct the original model. Okay, let's look at the coefficients, and the coefficients are all practically significant. And the AR3 is significant, the AR2 is almost significant, but even though it were not, we would have to leave it there. And the AR4 is barely significant, but it's really very close to 0.05. Remember, the 5% significance level is something arbitrary that's normally used, but I could consider this parameter significant. And the important thing is that my residuals are indicating a reasonably good fit for the model. Okay, was that clear? How you can correct your original model, analyzing the residuals and fitting a model for the residuals?
Yes, teacher, it's better now. Thank you.
Okay, great. Now what I'm going to ask you to do I'll split you in groups again. And I want to analyze a couple of series. One of them in particular will give you a little more difficulty in finding the right model, but now you know how to fix that, okay? Let me see which models I want you to. I want you to do this thing for the New Zealand air passenger data that you have in Brightspace. New Zealand air passenger data. These are monthly observations, and it's here. Let me go to this data. New Zealand air passenger data. Okay, use that. The New Zealand air passenger data has two different series. So I'm gonna read here, and it has arrivals. Okay, it has arrivals, and it has also departures. Okay, I need to analyze the arrivals series and find a model. You need to do the analysis, the forecast with the splitting the data, do a forecast of the last 12 periods, okay, a forecast of the last 12 periods. And let me read the file. I don't know if I read it here. Here it is. It has the date, arrivals, departures, and it's a monthly data. And if you see, for example, the series has 154 observations of the three variables. So I have 154 observations. So what I would want you to do is split the data. Split time series, both time series, leaving the last 12 observations for testing, feed the model, and forecast 12 observations in the future. Since you know the values of those data points, then calculate the RMSE and also do the forecast using exponential smoothing, the automatic method, and then do also calculate the RMSE. Again, it's better to calculate the RMSE and also the RMSE divided by the mean of the actual 12 last observations that we are going to forecast in both cases. Okay, pick those two series and do the analysis. The first one will be, you'll be able to find the model right away, but the second one is going to be a little bit more difficult. Okay, so I'm going to stop here and split. Actually, what I would want you to do, it's 10:45. Please start with the departures. Okay, start with departures because that's the one that's more complicated to find the model. So, in fact, only do the exercise for departures. Okay, you know now how to correct the model and find the best model. So do the analysis for departures and compare the exponential smoothing automatic forecast with the SARIMA forecast for departures for the departures data. Okay.